Welcome to our video lecture series flexible AC transmission system devices. This is our 10th lectures. In this lecture actually we will begin with, we will discuss about the FEX devices, and previous 9 lecture actually we were discussing mostly the power electronics, and now we shall start with the shunt compensation shunt FEX devices. So, my presentation layout will be following, that will be introduction, 2 machine system, voltage stability, transient stability and the power system oscillations and damping. These are the content, and we shall see that how it can be done by the shunt FEX devices. So, our discussions today will be on the shunt FEX devices. So, the main advantage of the shunt devices to support the reactive power demand, and our assumption is that this shunt devices does not contain any real power, but with the invent of the rather penetration of high level of distributed generations, this statement required to be state corrected, but till now in our initial assumptions we will assume that this FEX devices does not contain any real power, shunt power. So, for this reason what will happen, the major object of the shunt device is to support the reactive power demand, which will be actually oscillating into the power system. To increase the yield, the steady state transmittable power as well as stability of the system and the voltage profile required to be controlled, and it should be within a stable region. Shunt var compensation, actually it is a device that is used for the voltage regulation at the midpoint. We shall see the next slides how does it controls, or in some intermediate position it will be placed to the segment of the transmission line and at the end of the line to prevent the instability, as well as the dynamic voltage control will be placed. So, we will place it to damp out the power circuit oscillations that may arise due to the load change, or there is a fluctuations of the power supply, or due to maybe the huge fault. Now, consider the 2 machine system. So, consider the 2 machine system, and overall transmission line had a impedance x. So, it has been splitted in between x1 and x2, and this point the voltage is assumed to be actually Vn, and we assume that here angle is Vs minus delta by 2, here it is Vm, and here it is Vr delta by 2. And the transmission line represented it by the series line impedance of value x, and it has been splitted between x by 2 and x by 2 in 2 halves. And our assumption is that the sending and receiving voltages are Vs equal to Vr, that equal to V magnitude wise, and delta is the change of their power angle. Here it is minus delta by 2, here it is 0, here it is plus delta by 2, and this is the phasor, and where current I seems to be the perpendicular bisector of the voltages. Now, let us see that at the midpoint the power available at Pm equal is Ps should be equal to the sending end power, that is Pm into Vi, where Vm should be actually instantaneously it should be Vs plus Vr by 2, and we have assumed that Vs equal to there will be minus delta by 2. So, similarly we can find that this value Vm is 2 V cos delta by 2 by 2. Again I flowing this point to this point is Vs minus Vr by Jx. So, you substitute this value equal to I. Ultimately, from there you can derive the the reactive power available into the networks, that is Vi sin delta by 2, that is V square 1 minus cos delta by x. So, this is the reactive power in case of the in two machine model. So, maximum value of the power, we know that sending end voltage, receiving end voltage by the angle between them, sine of angle between them. So, maximum value of power will be V square by x, that is real power, and the reactive power will be 2 V square by x in this case. And most of the cases, practically delta we should restrict to the range of the 45 degree. So, otherwise there will be stability issues. So, we can find what is the stability issue, and thus it is not utilizing the proper power handling capability of the devices. So, and thus voltage profile also remains very poor. What happened, you can see that it crossed there. So, this is the point where the value is basically, in this case it is actually 90 degree. So, you have to operate somewhere here, this is 45 degree, and this value is your actually V square by x into root 2, 1 by root 2 should be the power. Similarly, this will be the reactive power, this line corresponds to the reactive power. So, how the reactive power can be enhanced, and thus how in this way we can increase the stability limit to the system. Let us see. Again, we shall continue with the two machine model, and the shunt compensation is been put at the midpoint. This is the shunt compensation, and it does not contain any real power, thus no power, real power is coming from the source. So, shunt compensation is represented by the sinusoidal AC voltage and the source in the source in phase with the midpoint Vm, and with the amplitude of sending and the receiving end voltage Vm equal to Vs equal to Vr equal to V. Similarly, so we can write from the previous phasor diagram. So, here Vm equal to Vs plus j I into x. So, this will be x by 2. Similarly, so you can rewrite this equation Vm equal to Vr plus Jm into x by 2. Thus, we can equate Vm both sides and see that what we will get. And at the midpoint, power is that is actually Vsm into Ism. So, from there we can see that if you multiply that actually Vsm, so it becomes cos delta by 4, and thus the power becomes 2 Vm square sin delta 2 by x. So, what happened here? You can see the stator way for though this angle is decreased, but power also been doubled. If you can increase somewhere the value of the delta, because you had a restriction to the value of delta, and you make the delta little bit more, and so you can also handle the power handling capability. Same way you can actually, let us talk about this QP. So, you will find that it is 2 V square 1 minus cos delta by 2 x. So, straight away we can find that this power equation has been modified. Now, let us plot it. So, with a normal fashion, this value will be V square by x sin delta, and with the midpoint shunt compensation, this value will be 2 V square by x sin delta by 2, and ultimately this will be the curve. and similarly with shunt compensation, reactive power becomes 4 v square by x 1 minus cos delta. So, straight away power handling capability had been enhanced by using a midpoint shunt compensation. Mind it does not generate any power, it increases the power handling capability. So, what is the takeaway from these discussions? The midpoint shunt compensation can significantly increase the transmittable power, both reactive as well as the real, and it doubles the maximum value at the expense of rapidly increasing reactive power demand at the midpoint of the compensator. And why midpoint? Why not at the beginning or at the end point? It is best location for the compensator. We can solve the problem and find it out where to be placed. This optimization will be studied some next classes, but we will discuss all kind of compensation, that is shunt compensations, series compensation, thereafter PAR, power angle regulators, thereafter you will find unified power quality or power quality conditioners, then internally power quality conditioners. Then we shall revisit these problems where it should be optimally placed, and we will find that the shunt finds the best position at the midpoint, because the sag voltage along the uncompensated compensation line is largest at the midpoint. That is the reason, and it breaks the transmission line into two equal segments for each, and the maximum power capability remains same each portion of the transmission line. Otherwise, some portion will have a more capability and some portion have a less capability, and thus you can continue to split half by half, and this in each compensation you can increase the power by 2. So, how many times you can split, that is an issue, but you also increase the cost of the putting the shunt devices. Moreover, the reactive power also get increased. To get better voltage profile, transmission line segment can be expanded to use multiple compensator, because you know that if you have terminated a capacitor, then voltage generally swells up a line. So, it is something like that, multiple capacitor located at the equal segment of the transmission line. Also, transmittable power would be double, that is what I was saying, doubling each of the segment. In ideal cases, constant voltage profile will be result as number of component as increased, but our assumption is that voltage profiles remain same, but it may not be same if it is a very long transmission line. So, for this reason, let us split this 2 machine model into 4. So, that what happened then? So, there will be a 4 segment, you can carry on each segment like previously done. So, ultimately it will be multiplied by 4 and delta, and its power transmission will be delta by 4. So, why we do not segment then? Generally, segmentation of the distribution network system is highly complex, and it is expensive, and it is not practicable also. The stability and reliability of the segment under appropriate contingency condition is also considered. However, the practicability of the limiter segment is the following. More importantly, this transmission line benefit the voltage support controlled by the shunt compensation at strategic location. That is very important. We require to compensate the voltage profile and the strategic network. So, it should, so that a consumer gets the better power, actually power qualities. And transmission system has been demonstrated by the numerous installation in numerous places by the fax devices. Now, let us see the how a shunt device can stabilize the voltage. So, let us consider a linear network, a simple radial system feeder reacting X. The nose point of the each plot is given a power factor represented by the voltage instability corresponding to that system condition, and voltage stability limit decreases with the inductive loads and increases with the capacitive load. So, you can see that what happened, this is a power handled by the system, and if it is load is inductive till this point, if you are increasing the inductive load, it degrades the value of per unit value of it, of the voltage. But if you transfer to the leading power factor, so this is the leading power from this onward, it is a capacitive, and you will find that voltage regulation is better. So, this is understandable that putting a shunt device in a reactive mode, in a capacitive mode, can help to restore the voltage or regulate the voltage in the sending end better. So, for this reason, generally shunt devices has been placed close to the sending end voltage. Shunt reactive compensation can effectively increase the voltage stability limit by supplying reactive power to the load and regulating the terminal voltage. What happened, the power required by this inductor, load inductor, can be actually compensated by the Shunt compensator. Thus, we will find the better voltage regulation, and ultimately you will find that this is the voltage characteristics. So, you can see that this is a unity power factor lagging, and thereafter what happened in case of the uncompensated line, generally this voltage generally swells up, and that touches the thermal limit and insulation limit and other issues. But shunt can ensure that this line is strictly at 1 per unit, and thus it increases the power handling capability of the line. So, this is strictly 1 and it increases the power handling capability of the line. So, this is a terminal voltage versus power factor or power plot. So, now we require to discuss about the voltage stability. So, we can see that it can stabilize voltage with the help of the shunt compensation. Reactive shunt compensation often used for the practical application to regulate voltage. To provide voltage support for the load, and due to the generation of the line outage, the capacity of the sending end system becomes impaired. The loss of the one power sources could be suddenly increase the load demand of the remaining part of the system, causing several voltage sag or depression, and that could result in ultimate voltage collapse, and those can be mitigated by the shunt compensation by better monitoring or regulating the voltage. Now, let us come to the transient stability. We have discussed transient stability in before, and now let us see how transient stability can enhance by the shunt compensation. Reactive shunt compensation can significantly increase the transferable power in the line. So, shunt compensation will able to change the power flow in the system under dynamic disturbances. If there is a slight increase into the power demand, then it can increase the power handling capability, and it can actually bring down this perturbation into the steady state limit. The potential effectiveness of the transient stability improvement can be conveniently evaluated by the equal area criteria that we are going to discuss in next class. The meaning of the equal area criteria, we have already studied equal area criteria in our power system stability and dynamics. So, same thing has been actually extended, and the meaning of the here equal area criteria is explained with the idea of the simple two machine model and the receiving end considered to be a infinite bus. So, this is the equal area criteria, and ultimately this is the load, this is the generation where it is matching. All of a sudden you have a fault or something, and due to that actually power demand increased, and this is A1 is your accelerating area and A2 is your decelerating area, and if you can stabilize A1 equal to A2 is a limit of stability, and previously you were operating del 1 and you should be able to actually close your breaker by delta 3. Otherwise your system will lose the synchronism. But in this case, as the power handling capability of the line is with enhanced to this, so it will from this curve Vm v square by x sin delta, this curve changes to v square by x sin delta by 2, and thus previously this A1 required to be A1, but with this shunt compensation AP1 and AP2, so that you can find that AP1 has a huge angle to clear. So, it can go as high as I critical should have been previously was 180 degree minus delta 1, here it should be equal to delta 1. Also power handling capability is double. So, there is a huge decelerating area to bring down the system in a controllable zone. So, what we can conclude? To assume that both the uncompensated and the compensated systems are subjected to some kind of fault for some period of time. For the prior to the fault, both of them was feeding the mechanical input was Pm and its angle was del 1, and during the fault the transmitted power becomes 0 and mechanical power become constant, and for this reason what happened? You have an accelerating potential, and this results of the sending end actually generator accelerates with a steady state with an angle delta 1 to delta P1 and to angle delta 2 to angle P2, and accelerating energies are represented by the A1 and AP1 respectively with and without fax devices. After fault clearing, what happens? The electrical power exceeds the mechanical power input and the sending end machines decelerates, the accumulated kinetic energy further increases until the balance of the power occurs, the area matches, until the balance between the accelerating area and the decelerating area matches. So, corresponding to the area for the energy balance is A1 and A2, and with the fax devices it is actually AP2, and where it is reaches delta 3 and delta P3. The constant Pm line over the intervals defined by the angle delta 3 and the delta critical, and to determine the margin of the transient stability, that is unused represented the area as area of the margin. So, you can see that this is your area of margin without fax devices, and this big chunk is the area of the margin with your fax devices. Thus, it makes the system stable with and its factor of safety is quite large. This is the advantage of the transient stability with the shunt control fax devices. Let us continue with the power oscillation and the damping. In case of the under damped power system, there might be a minor disturbance when there is a sudden change in load or any step change in load, or there is a certain small fault occurring, or any minor disturbance can cause a mechanical angle change around the steady state and thus gives you the torque angle ripple. This angle oscillation results for the actually oscillation also in the power. Since the delta changes, also the power changes. Sufficient damping can be a major problem in some power system and in some cases. It may be limiting factor for the transmittable power. So, we won't want that low frequency oscillation. Low frequency oscillation is very dangerous because power system itself is a low pass filter. So, it will allow this low pass low frequency power to be corrupt into the system, and it will be very difficult to actually and it will be very difficult to handle with this low pass low frequency power. For this reason, we require to actively damp out this low frequency, and it can be done by the shunt active power filter or shunt compensation. It is necessary to vary the applied shunt compensation here by the voltage of the transmission line and counteract the accelerating and the decelerating swings of the machines. So, what happen, it will come into the picture when this means that this power is actually, when it is more than this means this power is positive. So, power handling capability of the line required to be decreased, and thus it will damp out. And reverse we require to do in case of the when this d del t by dt is less than 0, that means it is decreasing the power, sin delta is changing, reducing, delta is reducing, and of course, the delta is around 45 degree. So, what you require to do when the rotationally oscillating generator accelerates at an angle delta and with the rate of change of angle is positive, the electric power transmitted must be increased to compensate the excess mechanical power input. Similarly, when it is decreasing, so gradually it will be actually reduce the power handling capability of the line. Otherwise, there will be a problem of stability. So, that is actually to damp out the actively damp out the transient. We shall continue in the next class with the power oscillations damping, and thank you for your attentions.